Okay, cool. Yeah, so welcome to Lecture 6. As I said last week and mentioned in the tutorials, the aim for this lecture is for us to now be able to start to evaluate FOL sentences. So that is, we're going to start to make sense of when they're true and false, and then using that idea, recover back all of the sort of semantic properties that we had for TFL. So the plan specifically, I want to start with introducing the basic idea of what we'll call interpretations. You can also call them models. It's basically the same idea. So we'll talk a little bit about what interpretations are. Okay? And in fact, I'll sort of give you a peek behind the curtain and tell you that so far, when we've been thinking about FOL, we've been operating with a simplifying assumption. And we're going to drop that simplifying assumption from today on. But we'll get clear on what exactly that is after we talk about interpretations. Once we have the general idea, we can then define truth and falsity for sentences in FOL. That will then set us up to define up semantic notions. And finally, we'll talk about the thing I'm going to ask you to do in the midterm, which is constructing your own interpretations to check for semantic notions. So how we can use interpretations to look for these various semantic properties. That's the plan. So let's get started by talking about what the hell an interpretation is to begin with. And recall when we very first started thinking about FOL 3 weeks ago, I emphasized that FOL has an increased expressive capacity. In particular, because of its grammatical structure, we can talk about particular individuals, or we can talk about groups. We can talk about at least one individual in the domain, everything in the domain, or using negation and an interplay, some portion of the domain. What we're going to do with FOL when we construct interpretations is going to basically talk about what predicates are true of. Because if you recall, the fundamental unit for FOL is a predicate and a term. Contrast that with TFL, right, where we just had the atomic sentence. Because in TFL we had atomic sentences, we could just say, is the sentence true or false? Well now, since our new fundamental unit is predicate term, it's going to be, is the thing picked out by the term an instance of the predicate? Is A an F? If A is in the F's, then that's going to be true. And if A is not in the F's, then that's going to be false. So the collection of objects from the domain that satisfy a predicate, we will call the predicate's extension. In this way, FOL is not a truth functional language. It's not like TFL. It's an extensional language. What's going to determine the truth or falsity of fundamental units is what objects from the domain are in the extensions of the relevant predicates. And then once we have those, everything else is going to work just like TFL. So that's the kind of background. It will be helpful to get this as we talk about how these things work. So let me start with a one-place predicate. We have the predicate capital T. Now, so far, we've been expressing these predicates by attaching them to bits of English, right? So T might be the kind of FOL representation of the English predicate is a teacher of the logic class. And then to see what the extension of the predicate would be, we go out and we look in the world, what object has that property? Or objects, right? There might be more than one. But that's a simplifying way to approach the extension of the predicate. This is how we fix the extension indirectly. We say the predicate is this property. Now we go and find the extension by seeing what things in the world have this property. But we can fix the extension another way. We do it directly. We say, here are the things that are in the extension by stipulation. And in this case, it would be just one object, me. So the difference here is hopefully clear. When we fix an extension indirectly, you hook the FOL predicate up with some property, you go and look to see what objects in the world have the property, and that tells you the extension. When we do it directly, we say, here are the things in the predicate. Here are the things in the extension. This is important because, again, we have been working with this simplified assumption that predicates track real English expressions. Is a spy, is a vegetarian, is a teacher of the logic class. Predicates don't have to be like that. Predicates are completely and totally arbitrary. Logic does not care about how well things fit together, in the sense of, okay, being a vegetarian is something like a kind of sensible class. Logic is strictly egalitarian. Any collection is just as good as any other collection. So that means we can fix the extension of a predicate however we like. We can make it such that the predicate T applies to everything in the domain. We can make it such that it applies to nothing in the domain. We can make it apply to just some objects in the domain that we fix by direct stipulation. So it's natural to think that FOL predicates are kind of like properties, English properties, but that's not the case. They're just simply predicates. We fix extensions however we like. So here's a way to kind of get a run up to that. Suppose we've got a universal domain. So absolutely everything that is, was, and ever will be is in our domain. We can then have the predicate Z, and we can stipulate by fixing the predicate partially directly and partially indirectly by saying Z is true of all and only the following things: me, the Eiffel Tower, and anyone who's ever lived in Tilburg. And then we can add some names, right? So we can have little n for me, little e for the Eiffel Tower. Note there'll be a lot of things in the domain we don't happen to have names for, but that's okay. We still know whether it's in the extension of the predicate or not. So on this account, right, Zn would be true on this interpretation. And it's true because the thing named by n, me, has been specified to be in the extension of the predicate. And we know this regardless of whether we know whether I live in Tilburg or not, which is the case, right? But it doesn't matter because we're told I'm in the extension of this predicate. And is this a very natural collection? No, but who cares, right? Doesn't matter. For us, for logic, the combination of things in the extension is whatever we want it to be. So again, Zn in this case is true on this interpretation because the thing named by n, Nathan, is in the extension of the predicate. Ze though, well, Ze in this case, is it true or false if we go back? Is Ze going to be true or false? It's true, right? It's true, because the thing named by E is in the extension of the predicate. There's the Eiffel Tower in the extension. There it is. So this is wrong, right? Typo in the fucking 5th or 6th page already. Way to go. But importantly, the lesson here, one-place predications where we have a name as the term are going to be true on a given interpretation if and only if the thing named is in the extension of the predicate. You might know this because the thing is just directly stipulated to be in the extension, or you might know it because you have to go out and look to see, does the object named have the property expressed if we're fixing extensions indirectly. Notably though, Zx is not true or false. It's not said anything yet. We need to know how to fill in the gap. What quantifier is being expressed here? Okay. So that's one-place predicates. What do we do with two-place predicates? Well, two-place predicates are going to basically be the same, right? We have else. We can read this as loves, so then we have to go out and look in the world, right? Does X love Y? Does A love B? Does B love C? Does B love A? Right? This would be fixing it indirectly. Or we could settle the extension directly. Here, though, because it's a two-place relation, we can't just stipulate individuals. We stipulate pairs, ordered pairs. So, for example, Finn loves Princess Bubblegum. Finn loves Jake. Jake loves Finn. Note, not in the extension, Bubblegum, comma, Finn. Because Princess Bubblegum likes Finn, but she doesn't love him. She loves Marceline the Vampire Queen, as everybody knows. Right? So what do we get then? We get these structures coming out true. Because this ordered pair is in the collection, right? Finn loves Princess Bubblegum. This ordered pair is in the collection. Finn loves Jake. But we don't get LPF. That will be false because that ordered pair is not in the collection. It's not in the extension here. And similarly, Jake doesn't love Princess Bubblegum either. That ordered pair is not in the collection. So when we think about extensions, if it's a one-place thing, is the object named in the extension? Cool, then it's true. If it's not, it's false. And when we're doing relations, is the ordered pair in the extension? If it is, the relation holds that way. If it's not, then it doesn't. This is going to be our base unit for truth. Predicate plus term will either be true or false if the thing the term denotes is in the extension, or if it's not. That's it. So again, we can say two-place predicate descriptions are a B, true if and only if the ordered pair A, comma B is in the extension. But that doesn't mean that RBA will be true, because that's a different ordered pair. It's a different ordering. Okay. So far, so good? Note, the other thing that we have to mention here is that identity is special. Because we write it specially to indicate that it is this special relation, we never have to fix the extension of identity. We never have to specify what relation the equals to sign is expressing. It's always identity, and its extension is going to be settled by, well, what things are actually identical or distinct. Every other predicate, though, is up for grabs. So we can now talk about what an interpretation officially is. An interpretation does three things. It specifies a domain. It assigns exactly one object within the domain for each name that we're thinking about. And for each predicate, excepting for identity, it tells us the extension. That is, what things from the domain satisfy the predicates. And it's this last bit that's kind of the most important part. By fixing extensions, it's telling us what objects satisfy or fail to satisfy the predicates, so fixes the truth value of the base units, which then will in turn determine what happens with all of the truth functional connectives, because they behave exactly like they did for TFL. So in this way, we fix extensions, and it indirectly fixes the truth value of the sentences by fixing the base units, and then so on and so on and so on. So again, an interpretation, domain, objects in the domain picked out by names if there are any, and extensions of predicates. Extensions of predicates being what objects from the domain satisfy which of the predicates. So here's a sample interpretation. Note it looks a whole lot like a symbolization key. But importantly, it's slightly different. We can fix the extensions of predicates indirectly, which is how we've been doing it, or it might fix the extensions of the predicates directly. Just telling us, here's the things from the domain that satisfy this predicate. And in fact, just to really point this out, in FOL, the meaning of a predicate isn't whatever English expression we associate it with, it is its extension. The meaning of Z here isn't some property. In fact, there's not really a handy English expression for that. But I don't care, because the meaning of the predicate just is this list of objects. And here's some fun things. We can have a predicate that's true of some of the objects in the domain. We can have a predicate that's true of every object in the domain. We can have predicates that are true of nothing in the domain. Predicates can be universal, they can be empty, or they can be just a fixed amount. So an example, right? Let's take the domain being people who are in this room. Right? The predicate being in the room will be true of every object in the domain. Being outside the room will be true of nothing in the domain. And in the front half of the room, that'll be true of some of the domain, but not all. Again, you see the idea. In that case, we're fixing the extension indirectly. But if we wanted to instead, we could just list everybody's name who satisfies the relevant predicates. Okay. Questions so far? Feeling okay? All right. Interestingly, we can also do interpretations via diagrams. These diagrammatic interpretations express relations. And you do it by simply labeling some nodes on a graph, and then the arrow represents the holding of a relation. So in this case, right, we can have the R relation be expressed by the arrow, and something like RAB is true because there's an arrow that starts at A and points to D. Sorry, I said B. Wrong one. Importantly, RAB in this interpretation is false because there is no arrow that starts at A and points to B. So it's just a visual representation of the ordered pairs that are in the extension of relation R. And another point, right? Again, since they're directed arrows, note RCB is false on this interpretation because there's no arrow that starts at C and points to B. So again, what can we do when we're building interpretations? To go back a slide, you can do it this way, where you list off domain, relevant names, and the extensions of the predicates, which can be settled either directly or indirectly. Or you can do a diagrammatic interpretation, where the domain is fixed by just simply being on the diagram, and we use arrows to express the holding of a relation. Importantly, when I'll ask you questions about constructing your interpretations, you can do either one. Draw the diagrams if you find it helpful, or write out the interpretation if you find that easier. Whichever one is fine, if it's appropriate. Okay. So, that's what an interpretation is. We can use interpretations to help define up truth or falsity for all FOL structured sentences. We've already got the basic one. If you have a predicate and a name, you know when it's going to be true or false. If thing named is an extension. All the rest are going to follow from that. So there's three kinds of sentences in FOL. Atomic ones, sentences whose main operators are connectives, and sentences whose main operators are quantifiers. We'll go through them one by one. For atomic sentences, I'm going to give you the fancy definition. Right? When R is an n-place predicate, and A1 through N are R number of names, or N number of names. R A1 through AN is true in an interpretation if and only if A1 through AN are in the extension of R. And I'm writing it this way because this captures not just one place, but potentially however many place predicates you want. Again, the basic idea is that FA is going to be true on an interpretation if the thing named by A is in the extension of F. RAB is true on an interpretation if and only if the ordered pair AB is in the extension. You can then extend this further. You see the idea, hopefully. Finally, with identity, right? A is identical to B if and only if A and B are the same thing. Easy peasy. So there's our basics, right? Atomic sentences are true in an interpretation or false in an interpretation according to this. What about the connectives? FOL sentences whose main operator is a connective. Forgot. I got this. We've got our diagrammatic interpretation again. This is the same thing we said just a second ago. And we have this, our non-diagrammatic, so written out interpretation. Again, here, ZN is true because I'm in the extension of the predicate. ZD is false because Vader is not in the extension of the predicate. Hopefully that's clear. So what do we do with sentences whose main operators are connectives? It works just like it did in TFL. The negation is going to be true if and only if the sentence it's applied to is false. The conjunction will be true if and only if both conjuncts are true. Disjunct works just like disjunction. Conditional works just like the conditional. And the biconditional works just like it did before. Those are easy. Again, you look to see about the relevant sentences, fix those, and then these behave truth functionally, just like they did before. So, we can give a quick rundown. Here's a sample interpretation. We've got every Simpson character ever, which is a damn huge domain. We have the predicate A, fixed indirectly as is an American. We have B, fixed indirectly as is a baby. O, a two-place is older than relation, and we have little m for Maggie and little h for Homer. So if we take this, what's the truth value on this interpretation of sentence 1, of our top sentence? On this interpretation, is negation OMH true or false? So let's think about it, right? Yeah. Cool, why? Talk me through it.
Because we have OMH and Maggie and Homer are in the so we can put it in the O, and then negation of truth is
Good, but let's think, right? Let's drop the negation for a second, come back to it. Is OMH true on this interpretation? It's false, right? It's false. Why is it false? Because in order for OMH to be true, Maggie has to stand in the is older than relation to Homer. Right? That's what O is taken to represent here. M is mapped to Maggie, and H is mapped to Homer. Cool? So we have OMH is false, because the object named by M and the object named by H do not stand in the O relation to each other. We see the idea. So if that sentence is false, then it hits the negation. What's going to be the value of our sentence? It's going to be true. It's going to be true. And again, it's worth kind of seeing, right? So why does it work out this way? What we do to evaluate OMH is we see, is the ordered pair M, comma H in the extension of the O relation? And Maggie's not older than Homer. She's the baby. That's the trick. So So our first sentence is going to be true because the sentence it's negating is false. Let's try our second one, right? We have BM conjunction OHM. So our main operator here is the conjunction. Yeah.
Is it possible to have false, like we have negation of false statement and it should be true, right?
Yeah.
So is it possible that negation of false statement will be also false?
No. Because negation is the flipper, right? It's truth functional. Whatever input value it takes, it then gives you the opposite value. So you cannot input something false to a negation and get a false out. That's important. Okay, so again, let's take our second one, our conjunction. The conjunction, in order to be true, needs both conjuncts to be true. So, are both conjuncts true? Is BM true on this interpretation? Is Maggie a baby? Yeah. Again, I realize this is old stuff, so it's hard. You might not know The Simpsons, which is saddening, but it's fair. Right? Maggie's a baby, so BM is true. And how about OHM? It's true as well. So then what is our conjunction? It's true. Again, we're starting to see it. How about our third one? OMH on one side and not AM on the other. So is Maggie older than Homer? Let's take our left-hand side. It's false, right? It's false. Maggie is the baby, Homer's her dad. And what about AM? AM is true. Yeah. Nice, right? Both sides turn out to be false. And then, of course, we hit the biconditional. And if the biconditional says both sides have the same value, it's happy. And our fourth one, our disjunction. Is our disjunction going to be true or false on this interpretation? So, in order to be true, right, just like before, disjunction's true if and only if at least one side is true. And is one of these two sides true? Easy, right? The identity claim has to be true. Because the thing named by H has to be identical to the thing named by H. We don't even care what that is. So, disjunction's true. And finally, our conditional. What's the truth value for our conditional on this interpretation? Whoa, so I heard some disagreement, right? So it's a conditional, and we can find out very quickly, right? When is the one-time conditionals false? Antecedent's true, consequence false, right? Every other time it's going to be true. And is our antecedent true or false? It's false, right? So it must be true. Again, what's the process here? How do we do it? Right? You start out by looking at the basics, the atoms. You see, are the things named in the extensions of the predicates? If they are, then the predication's true. And if they're not, the predication's false. And then all the rest of the stuff about the connectives works just like it did before. Cool? Please. So what the domain determines is what things we can then put into the extensions of the predicates. What will settle the extensions are either, right, if we're doing it indirectly, what things in the domain, properties they have. Right? So in this case, right, because we fixed a, say, extension of B is a baby, we have to dig through the domain and see which objects in the domain are B's. I mean, in a sense, because if we did that, right, obviously these would all be false.
No, I mean the Simpsons world.
Yes, yes.
The actual.
Yes. We need to, if we do things indirectly, if we fix them indirectly, we've got to go and look and see what are the things in the domain like. We have to know that, hey, Maggie is a baby and that Homer is a grown adult, right? So we have to know stuff. But we could also fix these extensions directly. We just simply list, hey, here are the list of things that are bees. Maggie, there's other babies, but I don't remember. That would be the idea. Okay, good so far? So note, we've already got 2 out of the 3 ready. We know how to do atoms, and we know how to do the connectives. All that's left are the quantifiers. So how are we going to do quantifiers? Well, remember what we've been talking about. The existential quantifier tells us at least one thing satisfies the attached sentence. And the universal quantifier says everything in the domain satisfies the sentence. Importantly, both of those are understood not in terms of what objects we have names for, but what's in the domain. And you can start to see it if you think about these cases, right? So we're going to use the same interpretation we had just a second ago. And when we think about, say, the existential, it's asking us not, hey, do you have a name that you could plug in for X? It's saying, is there something in the domain you could plug in for X? So a lot of times, the things we'll be talking about will outstrip what names we have. Just think about when we were using the universal domain. I certainly didn't list off an infinite number of names. So what we're going to do is basically say, hey, we've got our interpretation, and there's a bunch of stuff in the domain that we don't have names for, but we could have a name for them. So what we can do is extend our interpretation in some various way to add the missing names. We can start to see this if we think about these sentences before we dive in. So let's take our first one, right? Our first one. What does it say? What does the first sentence say? Someone's older than Homer, right? Someone in the domain is older than Homer. And can we think of anybody who's going to be in the domain who's older than Homer? I mean, there's Grandpa Simpson, right? He's Homer's dad, so he's going to have to be older than Homer, presumably. Right? There's Mr. Burns, who is shown in one episode as being ancient, walking around with the dinosaurs. I'm pretty sure he's older than Homer. Right? So one should be true. There's something in the domain that's older than Homer. In fact, there's several somethings. What about our second one? Our second one tells us there's something in the domain that stands in the O relation to Maggie and is not an A. So putting that in English, there's got to be something in the domain that's older than Maggie and isn't American. Is there going to be any of those? Yeah, I mean, one easy answer here, Groundskeeper Willie is older than a baby, and he's infamously and ridiculously Scottish. So 2 should also turn out true. But note, we don't have a name for him in our interpretation, but it doesn't matter because he's in the domain. And how about our third one? Our third one tells us everything in the domain is either in the extension of A or it's not. And that's just going to be true, right? That's going to be true. No matter what you pick, it's either going to be an American or it'll be something else. Even the space aliens. And finally, our last sentence. What does our last sentence say? So this time it's a little harder because it's got 2 quantifiers. But it tells us for every object in the domain, there's somebody who's older than them, right? For every object in the domain, there's someone older than them. That's going to be false, right? Because there's going to be somebody who's the oldest, or some people who are equally as old, right? No, that's just a kind of jokey version, but we start to see how this works. So I'll talk you through the idea of extensions, but it's important that you also just get the intuitive notion. The intuitive notion is the existential is going to be true if there's even one thing in the domain, whether we have a name for it or not, that we can plug in. The universal will be true if and only if every object in the domain can be slotted in, and it will be false if there's even one that doesn't make the sentence true. So let's go through them one by one. Here's our first one. Right? There's something in the domain such that X stands in the O relation to H. Okay, cool. Well, we can take Mr. Burns. We know that Mr. Burns is depicted as being ancient, clearly older than Homer. But we don't have a name for him here. But we know that he is in the domain. So we can extend our interpretation, adding a name that we don't have, to then pick out and name the object we know is in the domain. So we add an extension. You can see it in this orange color here. And our extension introduces the additional missing name to pick out the object. We can then plug that new name in for X, effectively plugging the object in, and we then get a sentence that's true or false. Does the object named by B stand in the O relation to H? Yeah, because Burns is older. Beautiful. So even though we don't happen to have a name for the object, we know it's in the domain, so we can extend the interpretation by adding the missing name to then plug the object in. So an existential will be true if and only if there's some extension where the thing named can then be plugged in. And our second sentence, right? Again, recall, it was supposed to come out true. So we can make it come out true by, again, noting there's got to be something in the domain. Groundskeeper Willie. There's the Mexican guy in the bumblebee suit. Similar kind of jokey example, but we know that there's an object in the domain, but we don't have a name for it. So we extend our interpretation, introducing the missing name, plug that in, and then we can read it off. The universal is a little bit more complicated. So our universal. Recall that this one, our third one, was supposed to come out true. So how do we do this? Well, it's the same process. We take our interpretation and we extend it by introducing a new name. But this new name is kind of a dummy name. It's not going to be mapped to any particular individual in the domain. Instead, it sort of allows us to refer to everyone. We introduce an extended name that's basically like an it. And then we see if we have this stand in for every object, will the name be true? So it's a name that stands for anyone, if you like. And then we see, hey, does this turn out true when we plug in A as the standing in for anyone, read it in the basic way, take it as if it's an atomic sentence, and that will then do the job. And importantly, if we find even one person that we can name with this extended dummy A, then the universal will be false. We can find one person we can plug in here that don't make this true. Which is what happens with our fourth one. So our fourth one, remember, this says, right, For everyone in the domain, there's someone older than them. And intuitively, this cannot be true because there's going to be either an oldest person or some people who are equally old. Yeah.
So then if you eventually remove all the names, you get only tautologies and contradictions.
So not just tautologies and contradictions, right?
Yeah.
Importantly, first thing, all of this is always relativized to a particular interpretation. And we can do whatever we like. We don't really need names for interpretations many times. We just need to have the objects in the domain and to fix the extensions.
Sure, but something will be true only by its form, right?
In a sense, right? So remember, what we're doing when we think about this is we're saying, hey, as long as there's some object in the domain, whether we have a name for it or not, to assess either one of our conditionals, we then need to be able to postulate an extension.
Sure.
So to go back, right? Take this one. We know there's something in the domain, even though we don't have a name for it. And that would be true also if we dropped these, replace them with variables as well. Right? All we need is, could we build an extension to our initial interpretation that adds the names?
Sure.
So it's still not necessarily going to give us just tautologies or something equivalent. I'll talk in a second. But it will give us a way to understand on this interpretations, is this claim true or false? Okay. So again, coming back to our fourth one, what do we do here? Well, we're going to do the extensions in two steps. We add a name A, and our A here is going to be, in fact, a kind of definite description. A will be the oldest character, the oldest person in the domain. And importantly, if we have A be mapped to whoever is the oldest in this domain, we then will not be able to find a name B that maps to anything in the domain where B is older than A. Or put in very strict terms, there will be no ordered pairs where A is in the second spot in the extension of O. You'll never get a O ordered, or sorry, A ordered pair. That doesn't happen. So again, what's the basic process for evaluating these? When we have an extension, look to see, is there even one object in the domain that you can slot in, whether you have a name for it or not? When you have a universal, look to see, can you slot every object in? If there's even one that satisfies the sentence, the existential is true. If there's even one that doesn't satisfy the sentence, the universal is false. Nice. So this is the basic process. I'm going to mention the slightly more complicated explicit formulation here, but if you understand what I just went through, you'll be able to assess these sentences. So the explicit formulation of what we're doing here. We have some sexy swash font expression A. It's a formula containing at least one variable A, or X, that's free. Right? We can then do what we'll call an instantiation or a substitution. Replace every occurrence of the variable with some name. Right? So we just basically take the variable and you plug in whatever name you want. Okay, so this gives us a substitution instance. We can then say that a universal claim is true in an interpretation if and only if we plug in a name in place of the variable. It doesn't matter what object C is assigned to, it will still come out true. Basically, again, the complicated version of saying you can replace the variable with any object you like. Similarly, we can say that the existential is true in an interpretation if and only if there's even one instance where we substitute in a name that makes it true. So again, this is just kind of getting our ducks in a row. What's important is that you understand the stuff I was saying previous couple slides about how to make sense of quantifiers. The existential is true if there's even one object from the domain. The universal's false if there's even one from the domain that you can plug in where it doesn't come out the case. So that's how we're going to get truth in FOL. We build interpretations. We then read off these interpretations whether the relevant formulas are true. The formulas then fix what we do with the connectives and also indirectly tell us how to make sense of the quantifiers. Now that we have this, what we can start to do is define up various semantic notions. So we're going to get notions that are equivalent to being a necessary truth, being a necessary falsehood, being equivalent, being jointly consistent. But now, instead of being defined in terms of interpretations, defined in terms of valuations, they will be defined in terms of interpretations. So that's the move next. But first, we'll take a break. We'll take, so it's 32. So should we go to 45? So 13 minutes? Cool. All right. Take a 13-minute break, and we'll come back from there.